Hello everybody. So in this video we're going to start with the calculations of the optimum pipe diameter that was kind of discussed in the previous video in details. So what we're going to do now is to do the fixed cost calculation and the operating cost calculation and the sum of them for many diameters, and we will draw the curve and see how we can get the optimum diameter. But before we go ahead and do that, I just want to summarize or kind of demonstrate what I have here. So I'm splitting the Excel file into three parts. This part is where I have the information that I'm gonna start with. I have here the first pressure or the pressure at point 1 and the pressure at point 2. These are the 2 points where the flow is going to flow from and to. And this is the heights of the 2 points, point 1 and point 2, the elevation. And I know that, so all the values are kind of assumed values. You can change the values if you want. But they're just for the sake of demonstration. The epsilon is the roughness of the surface of the pipe, which is 0.04 millimeters. The length of the pipe is 2000 meters. The flow rate is 750 liters per minute, and I have multiplied it or divided by it by 1000 and by 60 to be meter cube per second. So the reason I did this is because we're gonna use the SI units, so I have to make sure that the units are consistent. I'm using water, so the density is 1000 kilogram per meter cube. The viscosity is 10 power minus 3 Pascal second. And I know that the price of electricity is $0.05 per kilowatt hour, and the efficiency of the pump, I'm assuming it to be 65%. The project is gonna work 360 days per year, which correspond to 8640 hours per year, which is multiplication of 360 by 24, and the project lifetime is gonna be 10 years. So this is the first part, which is the available information about the project and the operating conditions. This part is related to the calculation of the fixed cost of the pipes or the pipe cost, which I consider as the only source of the fixed cost. I mentioned before that there might be other things like the cost of the pipes, the fittings, and everything else, but I'm assuming that the pipes are gonna be just pipes without any fittings, and the pump cost is gonna be or is not gonna be included, assuming that I have already a pump, which is not true, but this is just for the sake of simplicity. And in the next video I'm gonna add more details just to make it like step by step, complicating the problem. So I have here the table of the nominal diameter or the standards of the pipes. As we mentioned before, this is the nominal diameter, the schedule number, and for each schedule number I know the outer diameter and the thickness of the pipe, and I know the cost of each one of them as dollar per minute, per meter. So this is the unit cost of the pipes, or the unit length cost of the pipes. So this is what I'm gonna do for the fixed cost calculation, and this is the part for the operating cost calculations, and I don't have anything here. These are all things that we're gonna calculate in this video. So for the fixed cost calculation, it's very simple. I say that the cost of the pipes is the total length multiplied by the cost of unit length. So I know that this is the cost by unit length, and this is the total length. So it's gonna be this multiplied by this, and I have to make sure that I click F4 or before I drag, so that they are all calculated from the same length. So this is all for the fixed cost. Again, this is under the assumption that I have no other source of money or other thing that I have to pay as fixed cost. The calculations I'm gonna make are gonna be based on annual cost. So the electricity cost is gonna be annual cost as well. So I have to make the units consistent. So I have, this is the total cost for 10 years. So the share of each year is gonna be this divided by the project lifetime. So this is just to make sure that this and the fixed and the operating costs are both calculated from or the same way, on an annual basis. So this is this is the fixed cost. So it's pretty simple, straightforward, nothing tricky about it. Um, so now let's go to the second part, which is the operating cost. And the operating cost is longer, and or the steps are gonna be longer, and the reason it's gonna be like long calculations, because we have here the power calculated from the pump head. The rest of the terms are known to me, and the pump head is calculated from this equation, which is the modified Bernoulli equation, and we know everything except for the H losses, and the H losses are calculated from the losses equation. I know almost everything, but I don't know the velocity and I don't know the friction factor. The velocity is calculated from Q over A. The friction factor is calculated from this equation, which is function of epsilon over D and Reynolds number. And Reynolds number is rho Vd over mu. So I have to calculate the velocity, to calculate Reynolds number, and to calculate friction factor, and do everything. So it's gonna be like calculating something and then the next and the next, till we end up to have this equation calculated. It's not difficult, but it has to be done like step by step. So before we do that, everything is based on the area, and the area we know is calculated from the diameter. So I have to calculate the inner diameter, which we mentioned before. So the inner diameter is the outer diameter minus double the thickness. Um and this is in millimeters. As I mentioned before, I'm gonna use the metric units, the SI units. So I have to divide this by 1,000 so that it is in meters. So these are the inner diameters of the pipes that I have and that I want to pick from. I'm keeping the diameter in meters and in millimeters, because for all the calculations I'm gonna use the meters, except for one thing, which is the epsilon over T, which is this term, because I have epsilon already in millimeters. So there is no, for me, there is no need to divide this by 1,000 and then to divide it by diameter that has already been divided by 1,000 before. So I can keep the ratio as millimeters per by millimeter, instead of making this meter by meter. It's up to you. If you wanna unify all the units, it's fine. But I prefer to do this as long as I take care of the units and make sure that the units are consistent. So for the area, it's gonna be pi over 4 multiplied by the inner diameter power 2, and this is gonna be the same for all the diameter, the areas in meter and in millimeter. Um, Again, the areas should be very small in the very beginning and gonna be larger in at the end. For the velocity is gonna be Q, this in meter joule per second. I'm gonna click F4 because it's the same flow rate for all, divided by the area in meter square. And these are the values. Again, just to have a sense of the numbers, it's kind of a very expected thing to have the velocity very large in the beginning and very small at the end, because this is very small area and this is very large area. For the epsilon over D is gonna be the epsilon, again click F4, divided by the inner diameter, in millimeter this time. And again, I'm gonna drag it, and we have all the epsilon over these. Now we go to Reynolds number, which is the density, F4 divided by viscosity, F4 multiplied by the velocity multiplied by the inner diameter in meter. So these are the values of Reynolds number that I have. Again, it starts with or it's large numbers, not very large, but it's like 1 million or almost 2 millions, and it ends up with 30,000. And again, this is expected because this is calculated from very high velocity and this is calculated from very low velocity. So it's not a weird thing. Now we go to this part, to the calculation of the friction factor. We have already calculated epsilon over D and the Reynolds number, so we need to calculate the friction factor. This is not an equation that can be calculated or can be solved directly, so I have to do iterative solution for it. So I'm gonna assume a value of the friction factor, let's say 0.01, and I'm gonna calculate the equation and see if this satisfies the equation or not. most probably it's not gonna satisfy it, so I have to do the goal seek, so or iterative solution. So I'm gonna calculate this equation and put everything on one side so that the equation equals to 0. So it's going to be 1 divided by square root of the friction factor plus 2 multiplied by log epsilon over d divided by 3.7 plus 2.51 divided by Reynolds number divided by square root of the friction factor. So this is all. I'm going to do this for all of them before I start the solution. It seems that it's not the same, it's not right for any one of them. They're all giving errors, so I have to do goal seek for all of them. But before I do this, just to make sure that you understand what's going to happen um, in this file. So I'm now calculating the friction factor. I'm using it to calculate the losses, the pump head, and then the power, and then the electricity cost, which is the operating cost, and then to calculate the total cost. So just to keep in mind that if I change the flow rate, if I change the pressure, it's not the pressure, but if I change the flow rate or any other parameter that is affecting the friction factor, then all of them need to be recalculated again. So it's going to be a tedious process. So what I'm going to do is I'm going to record the macro and make it repeat the calculation steps without having myself doing this again and again. So this is the button where I'm gonna calculate the friction factor. I'm gonna assign a macro and I'm going to record now. It's calling it friction factor. Okay, so now it is recording. And you see here this is saying a macro is currently recording, so this is icon can also help to let you know that it's calculating. So I'm going now to do goal seek this to the value of 0 by changing this, and I'm clicking OK. So it's doing it now. What I should expect is that I'm going to repeat the goal seek for all of these like 15, 16 times. But we saw before that we can find a better alternative. So I'm going to stop the recorder and edit the macro. And as we said before, there is like some things here or some commands here that were recorded that I'm not interested in, like scrolling down and scrolling up and doing these things. So I'm going to repeat this line starting from G5 and G35 and F35 until I reach G51 and F51. Just copying and pasting. So to save time, I have already done this task before. I'm putting this here, and the goal seek is done. So it's doing the same the same calculation process for all of them without recording them separately. So what I'm doing now is just to click on the calculate button, and it's doing the goal seek for me without having to do everything by myself. So it's kind of nice thing, and we demonstrated that before, so we don't need to talk about it more. Now let's go to the H losses, which are going to be F multiplied by L, which is this, click F4, divided by the diameter in meter, multiplied by V power 2 divided by 2 divided by 9.81. So this is the H losses. I also like to make sure that the cells are calculated from the proper cells and that dragging didn't ruin everything, or I forgot to click F4 on one of the buttons, so it's nice. What I have here is that the numbers here are very large. I'm talking about I think this is 11 million or something, or 1 million, 1 million meters, which is like a very, very, very large number. And this is expected because the diameter is very small and the area is very small, so the losses are large due to that. And on the other side, the losses here are almost nothing because of the very, very large area. And now let's go to the H pump. It's going to calculate it from the modified Bernoulli equation. So I'm assuming that the area is constant on both sides, so I'm not calculating V1 or V2. Or they're gonna cancel out because the velocity is the same. So I'm gonna include only the pressure, the height, and the H losses. So the pressure is P 2 minus P1. This is in atmosphere, so I have to multiply it by 1.013 times 10 power 5 to make it in Pascal, and then divide it by the density 4 divided by 9.81. I forgot to click F4 here and here. So this is the first term, which is this. I said this is not going to be included, plus Z2 F4 minus Z1 F4 plus the head losses. So it's like very large number. It's almost gonna be the same number like the H losses, because this term is the dominating term now. While here you'd see that the height or the pump head is almost constant at the end, or very slight change, because it's now dominated by the other terms, which is the P minus P divided by rho G. So again, this is something that I should expect. Now finally we can calculate the power of the pump, which is the rho 4 multiplied by 9.81 multiplied by the Q, which is this, and again F4 divided multiplied by the H pump in meters. So this is gonna be everything divided by, or in the numerator, divided by the pump efficiency, clicking F4. So this is gonna be giving the power in watts. I want it to be in kilowatts, so I'm gonna divide it by 1000. So these are the outputs again, just to check everything is calculated from the proper cell. So I'm going well now. Again, just to analyze the values, the power is very large here, and it's very small here. Again, it's almost constant. So this is totally what I expect, and this is what we mentioned in the previous video in the curve, that's going to be starting very large in the operating cost in the small diameter. So the total power is going to be the power, or the total power per year is going to be the power in kilowatts multiplied by the number of hours per year, which is kilowatt hour. Oh, I have to click F4 here. And now this is how much power I'm gonna need in kilowatt hours per year, and then finally multiply it by the electricity unit price, and this is everything. So this is what I'm gonna pay as the operating cost, and this is what I'm gonna pay as fixed cost per year. I have already taken the values here from what I have on the fixed cost and the operating cost, just to have all the data in one table, to be easy for me to plot it. And this is what I see. Of course, the plot seems to be like something wrong with it, and the reason is, or the reason I cannot see all the details and the curve is going down and up and everything, is because the first few values are giving huge amount of money. So this is 921 million. So it's making the scale very large. So I cannot see the details of the rest of the values. So to make it logical, of course, I'm not gonna use like anything larger than the 100,000 per year, because they seem to be like very large values. So I'm gonna go for this just to show these values, and I can make it like this actually, so that I can see only the values that are logical. These values are not logical at all, so I'm using the values that make some sense for me and make the plot kind of understandable. And this is kind of very similar to what we demonstrated in the video before, or the previous video, about how the curve should look like. So you see, this is the operating cost, the fixed cost. The operating cost is going down and it's almost getting constant, and the total cost is first dominated by the operating cost, because it's very large, and then it's getting high due to the increase in the fixed cost. So this is what we need to get at the end, and finally we need to find out what is the minimum or the optimum diameter, the minimum cost. So it seems to me it's one of these 2 points, but I don't know exactly which. So we can find it here by manually looking here, and it seems that it's 11,000 and something. So it's the 6-inch nominal diameter. We can calculate them in an easier way instead of doing these calculations manually by finding the minimum of these total cost, and it's going to be 11286, which is this value. I might make it easier for me by asking it to tell me which diameter corresponds to this total cost. So we mentioned before that there is a function that's called match, and it's by what it does is that I tell it that I want to find where a specific value is in an array. And it's telling me that it's in like location number 12. So starting from here, 1 2 3 4 5 6 7 8 9 10 11 12. So this is its location, or its place in the column. And there is an index function which is giving me the value in a specific location in an array. So I'm gonna tell the index that I want to look up in this, or find in this array the row number 12, and it's telling me that this is the 6 inches. So I can take this and put it here. Oops, and put it here by combining the two functions together. So it's index of a match. And this is everything. So the file is now automatically updating itself. So for instance, if I want to change any of the inputs, so I'm going to start with 1 atmosphere instead of 5. So I will find that it didn't change, but the cost changed. If I do some changes, so the thing that will make a change that we can see is the flow rate, because it affects everything. So I have already 750, so if I make it 500, I have first to recalculate the friction factors, and you'll see that I now will need 5 inches. If I go for 400, then I should go for like maybe smaller diameter. It's not smaller, but let's go for 250. And now it's more optimum to go for 3.5 inches. If I increase it, make it for instance 1000, and recalculate the friction factor, then it's gonna be more optimum to use the 6 inches. So the file now is kind of easy to use, and the nice thing is that you just need to only press on this calculate button in case of changing the flow rate. Otherwise you have to worry about nothing, and the file will update itself automatically, so you don't need to worry about anything. So this is all for this video. In the next video, we'll see if we want to include the pump as a fixed cost, and maybe the fittings. What shall we do? So this is going to be the topic of the next video. Don't forget to save the file as XLM file so that the macro is saved. Otherwise, it's not going to be saved. Just a quick hint. So I'll see you in the next video, inshallah. Goodbye.